Now we continue with the last part of this lecture where we talk about how quickly the channel is changing over time. And this is given by the autocorrelation function. So recall from the first lecture that the autocorrelation function of a random process B is given by this expression here. So it tells you to what extent the channel at some time t is correlated with the channel a little bit later. And we will assume wide sense stationarity so that this autocorrelation does not depend on the time at which we computed t. Since the channel is complex, we need to make sure that we add this star here. So what I show in this figure here are two Gaussian processes that have the same variance and the same mean, but they have different correlation, right? So you see the red process is changing slowly, so the correlation will be high. And the blue process, or the whatever color this is changing very quickly, so it will have low correlation. If I were to make the histogram of the random variable, so I collect all of these samples and make a histogram. For the red case, it would look something like this. For the blue case, it would look identical. Oh, this was supposed to be blue. Looks identical. So this is exactly the same. So the distribution is the same. Of the blue case and the red case, but of course the autocorrelation will look very different. The autocorrelation function you can also plot as a function of delta t. So I have here a beta delta t, where I assume that the t doesn't matter in this case. Now for the red case, the correlation is high, so that means the autocorrelation would maybe look something like this. And for the blue case, the correlation is low, so that means it will look something like this. Right, so it becomes narrow or broad. And what's also important are these zero crossings. This means when the autocorrelation is zero, that means that the process becomes uncorrelated. Right, so the delays for which this process becomes uncorrelated are interesting because it tells you after this time, basically the memory in the channel is gone. Good, let's go to the bottom part of the slide. So for wide sense stationary processes, the autocorrelation function does not depend on t, so this t is gone. We could then compute the Fourier transform of this, and this is called the power spectral density. So it's just a Fourier transform of the autocorrelation with respect to delta t. So here are some more examples of wide sense stationary processes. Let's first look at the picture on the left. Is this wide sense stationary? Yes or no? Well, it cannot be because the mean depends on time. For that reason, it's not correct. The second one also cannot be because the variance depends on time. The mean is okay, the mean is constant, but the variance depends on time. The last one could possibly be a wide sense stationary process because both the mean and variance appear to be constant. And this figure on the bottom right shows again a process with high and low correlation, as I've shown in the previous slide. Good. Now it turns out that for the Rayleigh fading channel, you can compute this autocorrelation function in closed form. You can find the derivation in the book, but we will not go into detail on this, so I will just give you the final expression. So it turns out for Rayleigh fading, autocorrelation function is given by this expression, where this is a so-called Bessel function, which has as an argument the Doppler shift times the delay. And again, here you have the Doppler shift, and this c is a normalization constant. You can compute the Fourier transform of this, and this also exists in closed form and looks like this. So it is more interesting to plot both of these guys. So on the left, I show the power spectrum density corresponding to Rayleigh fading. And you see that it has a support between plus and minus, between plus FD, look here, and minus FD. So this means that if you send a tone, that this tone will be spread according to this spectrum. So there's this kind of spectral broadening that's happening. On the right, I show the autocorrelation function, so I just plot this. And I mentioned before that the zero crossings are important, so it turns out that this first zero crossing happens when FD delta t is about 0.4. And I can plug in what FD means and changes. This means that when V times delta t is 0.4 lambda, we have a zero crossing. Okay, so this means the channel will decorrelate after about half a wavelength. Or in other words, the channel is constant when I look at delay differences, time differences that are much smaller than 0.4 over FD. Okay, so this tells me in turn that something about the coherence time of this channel. So why is this important? This is important for a number of things. So let's say that if you move, let's say the receiver with lambda over 2, that means the channel is uncorrelated from what it was before. Right? And this, for instance, implies that when I have a receiver with multiple antennas, like here, and these are each spaced lambda over 2 apart, each of these antennas will see independent channels, because uncorrelated and independent is the same when the channel is Gaussian. And this will be useful in the MIMO lecture, but not right now. Okay, so let's look at the text. Both the autocorrelation and power spectral density can be used for simulation. And we'll see an example of that in a bit. The mobility causes spectral broadening, so you see this on the left figure. It can also cause spectral shifting if you don't have a line of sight path, so that means that a tone that you send with some carrier is shifted by amount of FD, and this is called spectral shifting. We see that the channel will be approximately constant for delta t is much smaller than the first zero crossing, so around here, around this peak, the channel, for those delays, the channel is about constant. Now, I should let you know that the notion of coherence time is sometimes misused. So in some papers, and I think also in this course, you will see that the coherence time corresponds to this first zero crossing. So that's the time for the channel to become decorrelated or independent. But this is not a very intuitive notion of coherence time. Coherence time should actually mean the time for the channel to stay constant. So for that reason, sometimes people use 1/10 of this value as meaning the coherence time. This is the time for the channel to remain coherent. So just be careful when you talk about coherence time that you know what you are talking about. It could be the time for the channel to become independent, or the time for the channel, the time during which the channel is approximately constant. Good, then we just have, I think, one more topic. So let's do an example. Suppose that you're moving at a certain velocity, v kilometer per hour, v meter per second, whatever you prefer. You have a communication over 1 gigahertz carrier, so lambda is 30 centimeters, and 1 megabaud transmission, so 1 megahertz bandwidth. And you're sending packets that contain 200 symbols, right? So, that's a packet duration is equal to 2000 over b. That's how long one packet lasts. And the question is, at what speed can we move to still have a near constant channel for each packet? So we want the channel to be constant within the packet, and how fast can we move for that? So I again recommend you pause the video and try to solve this problem. So then this becomes the solution. When b is equal to 1 megahertz, this implies that t, sorry, I don't know what's happening with my pen. T becomes 1 microsecond. Lambda is 30 centimeters. Since we sent 2000 symbols, that means that one packet lasts 2 milliseconds. That's the duration of a packet. And now what we want is that the distance traveled within this packet is much less than lambda over 2. right? So V times 2 milliseconds should be less than lambda over 2. And then we can solve for V, and we find that V should be much smaller than 270 kilometers per hour. So now if we take a factor of 10 of that, that means about maybe 30 to up to 60 kilometers per hour should be fine for the packet to see a constant channel. Okay, so again, let's say this is time. This is my packet, which contains 2000 symbols. This takes 2 milliseconds. And then if I move very slowly, the channel will change very slowly. So this is the channel. If I were to move at 270 kilometers per hour, then probably the channel would look something like this. So that means during the packet transmission that the channel could change, which is not what we want. I had some Matlab example as well. Yes, then I think we can go to Matlab. So let me stop sharing here. Share Matlab. Let's see, where is Matlab? Good, so I've prepared a number of Matlab scripts that you can use for this course. This is very small. This is the first script, so I generated this last year. This is simple examples to play around with path loss and shadowing. So first of all, let's generate some example of how we compute path loss and shadowing. So let's say we have certain transmit power, and this should have some unit. Let's say this is in milliwatts. References of 1 meter, distance to the user of 100 meter, a velocity, meter per second. Wavelength, this is then 0.03 meter, because once you decide that the unit for one thing, everything else have to follow these units. I can then compute this K value. I choose a certain bandwidth. I need to do this in hertz because I've chosen my velocity in meter per second. I choose a certain path loss exponent. I can choose 3 here. A shadowing variance of 6.8. Then I compute the path loss. So this is the received power after path loss. I compute the shadowing as a Gaussian random variable here that I then convert to the linear scale, and then this will be my received power. Because if my transmit power was 1, then my received power will be this, so 2 times 10 to the minus 12, which is very low. But I can, in dB, will be 10 log 10 of PR. Let's see if this works. I should run all of this. Okay, so minus 113 dBm. Now we will generate a Rayleigh fading channel. So we will generate 100,000 realizations of Rayleigh fading channel. The way that we do this is we generate a complex Gaussian random variable, and then we associate it with the power due to path loss and shadowing. Right, so the average value here is something 10 to the minus. Well, the average value should be the same as this 4 times 10 to the minus 12. Okay, this is the exponential distribution that you see. Yeah, this is the Rayleigh fading distribution, of course, exponential distribution of the power. Now we can see what happens when we put some mobility, in which case the channel would change slowly over time. So we choose here a certain symbol duration, TS is 1 over the bandwidth. So here I choose bandwidth denoted by W instead of B. This is the Doppler shift given the velocity and the wavelength. I generate a filter based on the Doppler shift. So this is kind of indicating how quickly the channel is changing. And I filter the original channel, which was IID. So this is this channel H of independent numbers. I filter it with this filter, and then I plot the result. So in blue is the original channel without filtering, so independent values. And in red, if you can see, this is the real part of the channel over time after passing through this filter. Right, and I make this filter the length based on the Doppler shift. So if the Doppler shift is really large, I have a short filter and vice versa. It's time to stop, but let's just finish this. I can then compute the autocorrelation of this channel. So this is what is shown here. So in blue is the autocorrelation function of the original channel. So it's 0 everywhere except at lag equal to 0. And then the autocorrelation function of the filtered channel has this kind of triangular shape. This is because my channel itself was a box. And then I can also compute the power spectral density of the channel. So in blue is the one before filtering, and in red is the one after filtering. So you see that it has a limited frequency range after filtering. So again, I will upload these slides so you can play around with those if you want. Let me try to go back to my slides. Oops. Good. There's one more topic that will be used in the tutorial sessions, which is the so-called level crossing rate. So we introduce two concepts. The level crossing rate is the average number of times that per second that the channel crosses a certain level Z. So it's how often the channel goes, let's see, in this direction here. And that tells you something about how quickly also the channel is changing. There's also the notion of average fade duration. It's the average time that the channel is below this threshold, so the average value of these fades. And it turns out for the Rayleigh fading with Clark spectrum, you can compute both of these in closed form, and this will be used in some of the examples. Good. Finally, we ended with today's lecture. So based on today's lecture, you should be able to distinguish wideband and narrowband communication based on the bandwidth. Derive Doppler shifts, be able to tell me what resolvable paths are, write down the general formula for time-varying channels, say the difference between Rayleigh and Weissin fading, and also compute autocorrelation and PSD of wide-sense stationary fading processes. Good, thank you, and see you for lecture number 4.